Hello, this is video 16, and I've been reading your mind again. I'm getting bad about that. You're thinking, well, we've been wallowing around in the bits and bytes for a long time now, and all we've done is just look at this sort of static data. It just sits there. It's numbers. Okay, big deal. Everything in the computer is nothing but zeros and ones, that is binary. But when are we going to do something with those? What about some activities or some operations? Well, funny you should ask. Let's look at digital logic. And I'm going to start with an observation way back over here. Observation at the lowest, which is where we are. We are at the lowest of the low. At the lowest, most fundamental level, a computer is really what? Really just a huge arithmetic calculator. A-R-I-T-H-M-E-T-I-C calculator. We knew that. All those numbers, and it's doing all those calculations. Oh, wait a second. It's even more fundamental than that. It doesn't even know how to do math. And make sure the ink is dry. Okay, X. It's really just a huge logic calculator. Thus, digital logic is what you look at when you look at the bottom. Can't go any lower level of how a computer does what it does. For us to be able to talk about that intelligently, I hope that's where we're headed. Definition. I need to define this thing, a gate. G-A-T-E. Unrelated to Bill Gates, that was just a coincidence. A gate is a tiny hardware device. D-E-V-I-C-E. A gate is a tiny hardware device that takes some small number of binary inputs I'm writing rather than talking. It's unusual for me, huh? A gate is a tiny hardware device that takes some small number of binary inputs, which means that we're only going to feed in zeros and ones, and produces exactly one binary output. Doesn't sound like it does much, huh? Produces exactly one binary output. Now we're going to be looking at gates for a little while, so I want this to really sink in, so I'm going to read it back to you one more time. A gate is a tiny hardware device that takes some small number of binary inputs and produces exactly one binary output. Here's an example. For example, some of the basic gates. Here's one. It looks like, to me, it looks like a light switch. Half a circle with a thing coming out on the right hand side and two things coming in. Not a light switch, it looks like a plug-in, plug into the wall. That's what it is. Two inputs, I'm going to label those without loss of generality, A and B. What's output on the other side is A and B. A logical operation. And in capital letters means that we're doing the logical and. Alternatively, we could write that as A dot B for reasons that will gradually become apparent, at least I hope they do. The data flow is this direction. In other words, we're feeding in two inputs, A and B, 0 or 1, and the output on the other side is A and B, whatever that logical operation is. And the X is in the way now because I want to put a box around this. I'm going to get in that habit again, keep saying, oh, this is important, this is important. I accidentally put a Halloween box around this, orange and black. But there. Now, we'll treat that picture as if it is the definition of the AND gate. even though we need to define its behavior with this thing called a truth table. The table of truth. Truth table shows the behavior for this for all possible combinations of input A and B. So the way we do this is, across the top, I put a double bar to separate A and B on the left-hand side over here. Those are inputs. I'll label them as such this one time, but don't forget, I'm not going to do this every time. Inputs and the output. A dot B. Now, the order of rows here, first of all, let me see. How many different possible combinations? I don't have to figure that out in advance. I know that if this is binary inputs, then 0 is one of the possibilities. I'll just do those. 0 and 0. Turns out 0 and 0 is still 0. Now, there are all different sorts of ways that we might want to start thinking about zeros and ones. That could be just plain old 0 and 1, representative of nothing but itself. It could also represent true and false, thus called the truth table. I'm in a boxing mood. I'll put that in a box as well. This is a truth table. We could also think of it as on and off, so maybe light switches. The light switches are off in both cases. Light switch A is off, B is off. If it were a 1, the other binary possibility, then it would be on. Now, here's the order. We put these, this is a 2-bit binary number. That's another way to view this. All possible 2-bit binary numbers are 0, 0, 0, 1, 1, 0, 1, 1. We always list them in that order, increasing unsigned order. No 2's complement in this chart here, not for the inputs. No, no, no. This is 0, 1, 2, 3. That's the order. Now then, now I can fill out the rest of the output, or at least I hope I can. If I can stop being so verbose. What about 0 and 1? Well, if we think of that as true and false, then they've both got to be true for and to be true. So that's also got to be false or 0. What about true and false? That's also false. It's not looking good over there. It looks like we're not going to be able to have any ons. Oh, wait, wait. If they're both on, then the output is on. Now, while I have that example still drying in whiteboard juice on the board, I'm going to take us on a little tour of an aside. I'll even close up the black marker and do the aside in a different color. There's a whole branch of mathematics that deals with digital logic and true and false and all that. Aside. This is called Boolean logic or Boolean algebra. Algebra is a scary word. I'll use Boolean logic. It is a branch of mathematics. Branch of math that views 0 as false, just like we're doing, and 1 as true to evaluate Boolean logic expressions. And yeah, we'll see some of those. For example, let's say that A, that I've represented as one of the inputs here, A is actually a statement in English. A is, I'm good looking. I'm so excited about that, I'll put an exclamation point in my fantasy land. B, I'm rich. Well, that's an even bigger fantasy, I'm afraid. If that's the representation of these two Boolean variables, A and B, then the statement A dot B, well, now it just gets ridiculous. A dot B is, I'm good looking and I'm rich. See how we play this game? We've got two individual elemental statements. Each one of those can be true, it can be false, and we wanted to evaluate A dot B. Well, what we've got here, believe it or not, is a summary of all possibilities, all possible ways that A could be true or false, B could be true or false, and then the result A and B. For example, let's call this first one the Dr. England row here. I'm not good looking. 0, I'm not rich either. 0. So this statement, A dot B, I'm good looking and I'm rich, that's about as false as it could be. There are no gray areas here, though. It's either true or it's false. So it's false. I'm not rich and I'm good looking. I'm not good looking. Oh, so let's stop talking about me. Okay, let's see. What about this? This can be the Warren Buffett row. This is kind of an insult. Sorry, Warren, you're not here to defend yourself. Let's say you're Warren Buffett. What about A and B? Now notice this statement, just because of its structure, we can't tell if it's A. We can't tell if it's true or false. We have to know about each of A and B individually. That's the whole point of this discussion here, by the way. So I have to know about the true or falseness of A and B individually to be able to say anything about A and B. So let's think about Warren Buffett again. He's not a particularly attractive person at this point, I'm afraid. Maybe for an extremely old gentleman, but he's filthy rich. Good grief. That's why it's easy for us to make fun of him, because he's so much richer than we are. So A is false for Warren Buffett, but B is true. Sorry, Warren, it's not true that you're good looking and you're rich. There's got to be both. Who is this? This is my only girl dog, Darby. Oh, she's a beauty. Good looking for her age. She's 17. She's not very rich. She would have had to inherit that from her dad, and I don't have anything to give her. So she's good looking but not rich. This is the Darby row. It's still false. Poor Darby. It's not true that she's good looking and rich. And the bottom row, I'm good looking, I'm rich. Let's see. Kim Kardashian? You grant me that? Kim Kardashian. Oh, good looking and filthy rich for whatever reason. A and B, I'm good looking and I'm rich. Ding, 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 we finally have a winner. So it's true for Kim Kardashian. It's false for me and Warren Buffett and Darby. We could be on any one of these rows. We just have to know the value of A and the value of B to be able to figure that out. I hope that was useful. So, since that was so useful, you'll be able to answer this ridiculously trivial question. Is this statement true or false? STMC for statement. Is this statement true? This statement right here, A dot B, or false? Answer? Well, we got a summary of all the possibilities. The answer is, it depends. And that really is the answer. It's not true because of its structure as a sentence in English. It's either true or false based on its elemental statements combined with a logical operation here, which we've represented with a gate. And if it seems as if I'm really belaboring this point, maybe I'm rambling because the caffeine hadn't kicked in, or maybe I'm trying to really make sure this makes sense because this is so important. Okay, now, all that dark green stuff up there, I hope you got that down because it's going to have to go. I want to leave this down here. This is, in its way for us, even more important than that. So, bye-bye aside. Why did I get rid of that first? Well, we need to look at some more of these. This is the AND gate. Here's another gate that will, without loss of generality, I'm going to stick with A and B, just so we can do the side-by-side comparison if we want to. A and B, and this one to me looks like a fish head. You can come up with your own metaphors. It's pointed on the right-hand side and it's got a curved backside. So see, it's kind of like a fish head, huh? Two inputs, the data still flow in this direction. Zeros and ones go in. What comes out the other side? A or B? Capital OR. That looks like it's all one word. Let me split those up. Lowercase a is the input. Capital OR, B. A or B. And that looks like a plus sign. That's the logical operation. That's shorthand when we start writing these Boolean formulas that look like mathematical formulas, but they're really all Boolean. The only possible values for the variables are zeros and ones. Now, let's see. To make it look like that, I'll put the arrow, and I'll put this one. That was the Halloween gate. I'll put this one in a blue box. How's that? Well, it's kind of blue. Island turquoise. Now, what does that do? You know what? We can fully define what that does for every single possibility if we put a complete truth table. Complete truth table for a gate with two inputs is always going to have exactly the same 4 rows of inputs. The only place the truth table could be different is in the last column in the output. So here's my truth table for the OR gate. Inputs A and B, double line to separate inputs from outputs. A plus B is what it looks like. 0, 0, 0, 1, 1, 0, 1, 1. I'm already bored with that. It's always the same. Same old, same old. Here's where things could get different. A or B. And if we go back and think in Boolean logic terms, rich and good looking, we could do the same thing again. I forgot which order they were in. Was it good looking first? Good looking and rich. Okay. This is me again. I'm still, if I'm neither one, then I'm not good looking and not rich. Neither one. Warren Buffett, if B was rich, I don't even remember. That was a Warren Buffett row, right? So B was rich. Warren Buffett is rich. It doesn't matter if he's not good looking. He's rich or good looking. See how that works? Or only 1/2 of it has to be true for the whole thing to be true. What about this? Darby. Darby's good looking but not rich. So Darby is good looking or rich or good looking. It sounds like I'm going to try to cover myself here, but it really doesn't matter because this operation is commutative. It doesn't matter if I said rich or good looking or rich because it's going to be the same backward and forward. Okay, on this one, rich and good looking, Kim Kardashian. Yeah, a winner all the way through. Look how much more liberal the or is than the and. And is real picky. I'm only going to be true if both of them are true. I'm false everywhere else. The or is much more liberal. Yeah, I'll take anything you got as long as it's not just false all the way across the board. So or is true if either A or B or both are true. So far so good. Now, with such inefficient use of board space, I'm afraid I'm going to have to erase this and put another one here, and I'll use that as a model. Whew, how that works. It's like a chain. A chain of gates. The next one only has one input. And the silly little explanations I make to myself, that looks like a sideways clown hat, or maybe a birthday party hat. One input A. The output over here is not, N-O-T, not A. And the way we write that is an A with a bar over it. Complement. Sometimes called a complement in the Boolean logic world. And again, we're moving this direction just so that all our gates look alike. And who have I not used? I did use orange. I haven't used pink. So we'll put the birthday party hat in a pink box. Just to mix it up a little. Okay, truth table, yes, okay. Now this truth table doesn't have much to it. Actually, it has a little more to it than that. But since I only have one input, I'm only going to have 2 rows. 0 and 1. The output is the opposite of whatever A is. Not means if it's true, make it false on the output side. If it's false, make it true. So we just invert this. 0 input, then 1 output. 1 input, then 0 output. The end. Now, I don't want to get in too big a hurry here, but let's see if we can generalize this just a little bit. If I've only got 1 input, then there are only 2 possibilities. The truth table will always have exactly 2 rows for a one input logic function. Two inputs, there'll always be exactly 4 rows. 3 inputs. Yikes, how could we even figure that out? Think about this real hard now that you are binary representation of numbers experts. This ranges through all possibilities that I can represent in 2 bits. 0, 0 up through 1, 1. 0, 1, 2, 3. In 3 bits, I have 8 possibilities. 3 zeros, which is 0 on our place value chart, up through 3 ones, which is 7. Count with me real fast. 0, 1, 2, 3, 4, 5, 6, 7. That was 8. 8 different possibilities. Oh, wait. 4. Now we're getting just ridiculous here. What if we had 4 inputs? Actually, we're going to look at some that have 4 inputs. Not gates, but logical functions. Yes, A, B, C, D. Starts with 0, 0, 0, 0. 4 zeros. 4 ones. If you remember that, 4 ones, also known as hexadecimal F, is 15. And since we start counting at 0, that's a grand total of 16. What's the pattern there? What's the moral of the story? Every time we add one additional input to a truth table, we double the number of rows. If we start with 1 input and double the number of inputs, that's just only go from 1 to 2. That's not a big deal. But it doubles the number of rows from 2 up to 4. If I had A, B, C as inputs, there are 3 input gates, even a 3 input AND, a 3 input OR. They behave exactly the way you would expect them to. But if I go up to 3 inputs, then all of a sudden I double the number of rows from 4 up to 8. Solid zeros through solid ones, where solid ones would represent 7. Now, that's kind of looking a little bit into the future. We will look at truth tables that are that big, and I will always put them in the proper order. We've got to put them all in the same order because there are actually some operations, believe it or not, there's some operations that we're going to perform on truth tables once we get the gears turning and head toward our, dare I break the seal on mentioning it, our project 1. We're almost smart enough to do a cool, non-trivial, big project that involves binary numbers, digital logic, and all that stuff. Oh, I just can't wait. I know you can't either. Now, what have we looked at? 3 gates so far, and, which is noticeably absent on the board now, or, covered that, not. Okay, roll our sleeves up. Here's an observation. Let's get going on this. Great. That's an observation. So, when do we get to the, I'm going to call it heavy duty logic gates? What does that even mean? I don't know. I just made that up. When do we get to the heavy-duty logic gates? Like Pentium processor. Processors and stuff. Stuff is not the technical term. When do we get to the big logical operations that can really do non-trivial things? Fantastic, strange, wonderful calculations and all the things that computers have to do. When do we get to the big building blocks where we can talk about non-trivial computation? That was a question, form of a question. So I'll put a Q up here for question so that I can put an A down here for answer. Surprise, we're already there. A-L-R-E-A-D-Y, already there. Do you remember that just unbelievably miraculous statement that I said long time ago now, that anything that's represented in the computer has to be represented with zeros and ones? That's the only kind of data it can use. Whether it's a DVD of a movie, or it's your favorite song playing on your MP4 player, MP3 player, whatever it may be, it's all zeros and ones. You know what? The same miracle is occurring with respect to operations here. Anything a computer can do, anything, underline, anything a computer can do can be done using only and, or, and not gates. Can be done using only, that's a double underline emphasis, only and, or, and not gates. Exclamation point. And I didn't leave room there, but maybe I have room over here. I'll use red. It's alarming, exciting, all that stuff. Here. And or, I'll squeeze it in the middle up here. That's not a good idea. Maybe you want to write it down here. But I'm going to put it right here because I've got more room here. And or and not. Are what we in the biz would call logically complete. L-O-G-I-C-A-L-L-Y. Complete. What does that even mean? It means this. It means anything a computer can do can be done using nothing but huge numbers, millions, I don't know, maybe even billions, of and or and not gates connected in ways of all kinds of Boolean logic, formulas and all that stuff. But that's all you need. If you're stranded on a desert island and you don't have a computer, so you can't play computer games, and a big box of and or and not gates washes ashore, you're in luck. It might take you a while, but you can build you a computer, a complete computer. I don't know. I don't know how to make that sound any more important than it is. I can put it in a box since today's Boxing Day. And or not are logically complete. Now, I'm going to let you ponder the philosophical implications of that as we transition from this video to the next one. I'm not going to be able to prove this beyond any shadow of a doubt in your mind, perhaps, but I will show you that we're not missing anything. If we can think of a logical operation to do, pardon me, we can build it. These are our Lego blocks now. We got 3 flavors of Lego blocks, and or not. We can build anything we want. Any kind of logical operation. What sorts of logical operations? We could do addition, for example. Addition is built up from and or and not gates, and nothing else. I'll see you online.